So, we're wading our way through chapter 14. Likely, we're going to need more than just today. So, I will adjust the syllabus on the fly. Due dates are all way long anyway. I'm sorry for the. You may perceive this as lack of organization, but I'm just adjusting the pace so we can go to the appropriate depth. All right. So, we had talked about how to formulate our guess for what the wave function should be. We're using the idea of a simple molecule, perhaps hydrogen A bonded to hydrogen B. And we're going to guess that the wave function for the molecule is going to be a combination of wave functions from each individual atom. In this case, one from hydrogen, one from the other hydrogen. Now, if the molecule were bigger, this would be a whole lot more complicated, but the principles are the same. We talked about how you isolate energy from the Schrodinger equation. You end up having to apply the Hamiltonian to the wave function, multiply that by the complex conjugate of the wave function, integrate that overall space, and then divide by this integral, which is the wave function's complex conjugate multiplied by itself. We said that we've defined this number as equal to 1. In the end, we're going to come back and use that to get actual values for what these coefficients should be. At this point, we know what phi A and phi B are. These are like the 1s orbitals from hydrogen. So we just want to know how much of this orbital that we have comes from phi A and how much of it comes from phi B, and that will be weighted according to what these coefficients are. So jumping a few steps ahead in the math, we wrote this as sort of the expanded integral for energy. We had to define some terms. Ca and Cb are just the coefficients from here. HAA is the what's called the core integral. This is the Hamiltonian applied to phi A multiplied by the complex conjugate of phi A, and it gives you the energy of an electron in an atomic orbital that's not involved in bonding. Because A and B are both hydrogen, HAA and HBB are identical to each other. The HAB term and the HBA term are also identical to each other, but these reflect the energy of an electron shared between A and B. Interestingly, that's what happens when you apply the Hamiltonian to phi B and then multiply it by A and integrate. And that's called a resonance integral, with the idea of sharing an electron between two nuclei. I'll point out that these are energy numbers. They should be negative because it should be favorable to be held near a nucleus or favorable to be shared between two nuclei. So that will become important a little bit later as we consider some implications of the energy values that we get out. We'll need to be able to tell which one is more favorable than the other, and remembering that these are all negative numbers will help. Finally, S is the overlap integral. This is what you get when you multiply phi A by phi B and then integrate. And this describes literally how much phi A and B overlap in space. So if the bond is shorter, you'd think the overlap would be higher, and so on. Of course, phi A times phi A integrated overall space should be equal to 1. So with all of that in mind, we expand that out and get this messy equation. And now we want to know what Ca and Cb are. But we want to choose values for Ca and Cb such that the overall energy is as small as possible. That's a minimization problem, and when you do that, you use calculus. You take the first derivative of the energy with respect to Ca and set that equal to 0. And then we're going to solve that equation for Ca, and we'll know that if we can do that, whatever value of energy we get with that value of Ca should be a minimum. We'll do the same thing with Cb. So I'm not showing you taking the first derivative of that function with respect to Ca and Cb. You have to use the quotient rule, and if you want to see it, it's in last year's notes that are on the content page of Learning Suite for Chapter 14. Instead, I'm going to show you the equations that we get out. So the first one, which is based on differentiating energy with respect to Ca and setting that equal to 0. The first equation looks like this. Ca times HAA, that's the core integral, minus energy, plus Cb times HAB, that's the resonance integral, minus energy times S, which is the overlap integral. And we're going to set that equal to 0. Our second equation that we get is differentiating with respect to Cb. And again, I won't take you through that. If you want to see it, it's in the notes. But we get Ca times HAB, the resonance integral, minus Es. And then we get Cb times HBB minus E. And that's of course equal to 0. And I'm going to make things a little bit easier on us because remember we said that the core integrals for hydrogen A and hydrogen B should be identical. So we're going to just reduce the complexity of our equation here and substitute in HAA for HBB. All right, we now have a situation where we're assuming that HAB, HAA, S, and then E are all constants, whereas the coefficients are unknown. We've got two equations and two unknowns. And if you like matrices, which nobody actually does, right? I think we all learned about matrices and then promptly forgot about them. Maybe, I'm sorry if I'm offending you, maybe you really enjoyed linear algebra, and then I say more power to you. I took it in 1997. And boy, there's not a whole lot that's remained with me. 1997. None of you were even alive then, maybe. Oh, you were alive in 97? Okay. All right, good. Yeah, good. Good music from the 90s and the 80s, I guess. Anyway, you can represent this system of equations as a matrix. So we're going to take all the terms in parentheses and make this matrix out of them. And then we'll multiply that by Ca and Cb. And that's going to be equal to this matrix. Now, shoot. If you have a hard time seeing how what I wrote above is related to what we wrote here, just remember when multiplying matrices, you go D plus D, right? Sort of, right? These terms multiplied by each other plus these terms multiplied by each other equals 0. And same thing on the bottom. Okay, so as we look at this, and we want to solve for A and B, we're in an interesting situation. There's actually a trivial solution for this equation, and that is to set Ca and Cb equal to 0. But that's boring, right? Because of course, if Ca and Cb equal 0, both of these equations are true. The only way for this to have a non-trivial solution, and this is a principle from linear algebra that I don't intend to justify because I don't understand it, the only way to find a non-trivial solution if the determinant of the matrix, there's another unfortunate word, the determinant of that matrix is equal to 0. What do we mean by that? We symbolize the determinant, if you remember from linear algebra, with these vertical lines. I'm struggling to remember conceptually what the determinant means. If you're dealing with geometry, it can give you the area of space mapped out by a couple of vectors. In any case, we only have non-zero values for Ca and Cb if this determinant equals 0. All right. Well, how do you calculate a determinant? Brief review from linear algebra. You multiply A times D, and then you subtract B times C. Okay? So this is your A term, your B term, your C term, your D term. So that equation would turn out to be HAA minus E times HAA minus E minus HAB minus ES times HAB minus ES equals 0. Okay? So we can do that, and if you do that and solve for energy, you can get the following expressions for the energy: HAA plus HAB divided by 1 plus S. And then the second solution is HAA minus HAB divided by 1 minus S. Okay, those are your two energy values. We still don't know what the coefficients are, but we now know what the energy values are that allow those coefficients to exist and be minimum. Let's talk briefly about these two energy values that we get that allow for real and non-trivial solutions for those coefficients, CA and CB, from our wave function. I told you that HA and HAA and HAB are negative numbers. So which of these numbers has a lower, more favorable, more negative value? Solution A. So this is the stabilizing solution. Or we could just say that this is the lower energy solution and this is the higher energy solution. Remember how I told you that when we mix atomic orbitals together, we get as many molecular orbitals out as we have atomic orbitals in? This is where we get that idea. There are two possible energies that satisfy the equations that we've set up so far. This is the lower energy one on the left and the higher energy one on the right. And in fact, we will call the lower energy one a bonding orbital, and a higher energy one we will call an anti-bonding orbital. Now, there's an interesting consequence. This overlap integral here plays an interesting role. In sophomore organic chemistry, you may have been taught this idea that if I bring two 1s orbitals from two different hydrogens together, I get a bonding orbital, and there's some energy difference here, and then I get an anti-bonding orbital, and there's some energy difference here. This is the sigma bonding orbital, this is the sigma star, and you may have been told that at least to a first approximation, those energy differences are the same. That the bonding orbital is lower in energy than the starting orbitals, and the anti-bonding orbital is higher in energy by about the same amount. That's an oversimplification that I learned about when I first started teaching this class. It turns out that the effect of this overlap integral, let's see what that would do. Imagine that the overlap integral, let's say it's like 0.2 or something like that, okay? So first, let's imagine it's 0. Let's consider that case, right? If it's 0, then the energy of the bonding orbital is HAA plus HAB. Now let's let it be something not 0, like 0.2. That would tend to make this energy greater or smaller if you're dividing it by 1.2 instead of 1. It should be smaller, less stabilization, right? So the effect of S is to make this delta E number for the bonding orbital a little bit lower than expected. How about on the anti-bonding term? If S is 0.2, the denominator goes to less than 1. So if we're dividing by 0.8, what's the effect going to be on this number? Is it going to be lower in magnitude or higher in magnitude than it would otherwise have been?
Higher.
Higher. Remember, HAB is a negative number. Minusing a negative number is like positive number, right? So the effect of that overlap integral is to make the antibonding orbital even more destabilizing than the bonding orbital is stabilized. And this is a general principle that we're going to use again and again in physical organic chemistry. It's this idea that if we bring two orbitals together, and they can be any orbitals, we could be thinking of a pi bond. We'll just call this phi A and phi B to be as general as possible. We have a bonding orbital here. We'll call that psi 1. And then the anti-bonding orbital is up here, psi 2. And we're going to see that the stabilization associated with psi 1 is going to be lower than the destabilization associated with psi 2. Maybe we'll call this 1 and this 2. In other words, and you have to use absolute values here because you got sign comparisons, but the antibonding orbital is always more destabilized than the bonding orbital is stabilized. That seems a little bit... No, that's actually how I wrote it in my notes. Can we say that more clearly? I don't know. The antibonding orbital is always more destabilized than the bonding orbital is stabilized. Okay. What does this mean? This is the origin of something that is called closed shell repulsion. That is, if I have two electrons to give to this, to fill in this molecular orbital system, those two electrons are going to come here and they're going to experience stabilization. If I start with 4, I'm going to fill both the bonding and the anti-bonding orbitals. And I'm not only going to cancel out the bonding orbital, but actually I'm going to make it even worse. So now it's even worse for those two atoms to be close together than it would be for them to be infinitely far apart. This is, by the way, why hydrogen forms H2, but helium does not. It's called closed shell repulsion. And it's behind steric repulsion and van der Waals radii. It's behind this idea that atoms can't get, there's electrostatic repulsion, of course, but if you bring two filled orbitals close together and overlap them, that is always a bad thing. Okay? So questions about that? Now that just comes from the math that we've been talking about, but it's an interesting principle that we can use again and again. Yeah.
So when you say overlapping the orbitals, you don't mean like creating a bond?
Yeah, I do.
Okay.
Yeah, so you can't create a bond between two filled orbitals.
Oh, okay.
Yeah.
Okay.
Yep.
Gotcha.
What else? Okay, so we've got these two energy levels that are solutions to our setting our determinant equal to 0. And remember, we needed to do that so that there could be a non-zero solution for what Ca and Cb are. We're not going to do this now, but you can plug these values for energy back into these two equations or into this matrix, and you can solve for Ca and Cb. I'm not going to do that, but one could in principle do it. And when you do, you come to the following conclusion. For our molecule that we formulated in this way, where we let our molecular orbitals be a linear combination of the two atomic orbitals, and we've got these two different energies that we've talked about, one being bonding and the other being anti-bonding. If If you plug this back in, you come to the conclusion that CA equals CB. By the way, that's why the determinant was equal to 0. Alternatively, over here, you come to the conclusion that CA is equal to the opposite of CB. Now, this agrees qualitatively with a picture of bonding that, again, you may have been taught in a sophomore organic class. We talked about the bonding orbital coming from a 1s orbital from hydrogen A and a 1s orbital from hydrogen B overlapping with the same mathematical sign to give you, if this is hydrogen A and this is hydrogen B, a sort of sigma bonding orbital that looked like that. Whereas the anti-bonding orbital, we said, I used to teach, came from bringing the two atomic orbitals together out of phase to give you an anti-bonding orbital that looked something like this. But it turns out that this is exactly the solution you get from these two energies. You're told that there should be the same amount of, of the two possible wave functions, you're told that in the first one, the lowest energy one, there should be the same amount of orbital on atom A as there is on atom B, which makes sense because hydrogen's a symmetrical molecule. Your higher energy option is where you have the same amount of wave function but opposite sign. And because they have opposite sign, to get from one side to the other, you had to go through a spot where wave function equaled 0, which is a unique property of electrons being waves, right? It doesn't make any sense for matter to equal 0 yet. If you allow matter to have wave-like properties, there will be places where it goes to 0, just like in the standing wave or the particle in a box problem where we saw there were places where the wave magnitude equals 0. That's true for the anti-bonding orbital as well. Okay. Questions so far? Now, if you want, then you can let the first orbital that we made, we're going to call it Ca times phi A plus Ca times phi B, because Ca equals Cb. And then our second orbital is going to be Ca times phi A minus Ca times phi B. If you do that and then set those integrals equal to 1, we're not going to do that in class, but if you do that, you can actually get values for what those coefficients should be. In the lowest energy orbital, it turns out to be something like this, where S is the overlap integral, and that's also equal to CB. And then for the higher energy orbital, you get this answer. And the magnitude of the answer isn't important. Just notice that the coefficient is related to the extent of overlap, and you can get those coefficients from this assumption. And the process of using this assumption, setting the wave functions equal to 1, the wave function squared equal to 1, is called normalization. Why did we use quote marks and then parentheses? I don't know, just to be confusing. Okay, so we've done this for a very simple molecule, done it somewhat by hand. We're never going to do that again, though you can do it. We're in general going to let the computers go through this process for us, but the principles are going to be exactly the same. Okay, questions so far? All right. Yeah? No? Okay. You just had your hand there, I thought. Okay. Now, last time I taught this, I'm going to show you the notes. There's a lot of algebra, and it's terrible. This whole analysis was based on combining two orbitals that are equal in energy. All right? But of course, molecules that come from orbitals that are equal in energy are somewhat boring in the sense that maybe like hydrogen, you can burn them, but there's a limited number of reactions you can do with them. We're going to be interested in a lot of different molecules, a lot of different kinds of bonds where orbital energies are different. So we could ask the question, what if phi A and phi B are not the same? What if there's some energy difference between them? In other words, you recall when we above, we said that the Hamiltonian for phi A was equal to that similar Hamiltonian term for phi B because they were equal in energy. We said HAA equaled HBB, and that made things a little bit easier. But what if there's some energy difference between the two? And we don't know what it is. So you can go through everything we just did with this complication, and you can calculate what the coefficients should be and what the energies should be. And I won't show you the math, but I will tell you that the energy of, you're still going to get two orbitals, and they're still going to have, there's going to be an energy of a bonding orbital and an anti-bonding orbital. But the coefficients and the energies all depend, in addition to depending on HAA and HAB, they also, and on the overlap integral S, they also depend on that energy difference in a way that's pretty straightforward to understand once you've seen the result. Okay, so I won't go through the math. I did this the first time because I wanted to prove it to myself. I spent a large amount of time working on it and eventually had to use Mathematica to find solutions because it was just painful. But I think it's best to demonstrate this with a particular case. So let's imagine that phi A is some kind of p orbital, and phi B is also some kind of p orbital. But let's imagine they're on different kinds of atoms. We're going to learn later that more electronegative atoms have lower energy atomic orbitals. So we could suppose, for example, that HA came from some carbon, and that phi A came from some carbon, and phi B came from an oxygen. Oxygen's more electronegative than carbon. So we would say that in terms of starting energies, phi B is probably a little bit lower in energy than phi A. Okay? What happens when we mix those two together? Just for the sake of argument, I said for this analysis, and the reason I'm doing this is just to make everything to scale and to be as quantitative as possible. I said, let's let our starting energy equal 0, just arbitrarily. And that's the starting energy for phi A. Let's choose some value for HAB, which is the resonance integral, and somehow I chose -6. I don't know why. There's no units there. It's just -6, okay? The numbers aren't important, but I'm writing them down in case you decide to go back and try to reproduce this. Let's say that the overlap integral is somewhere between 0 and 1, let's say 0.2, because p orbitals are side to side, but side to side overlap isn't as good as end to end overlap. All right, so we're going to consider three cases. We're going to let these starting conditions be here, and then we're going to let the difference in energy between A and B, we're going to start where it equals 0. Then we're going to let it equal 2 energy units, and then let it equal 6 energy units. Okay? So when you do this, let's see, and I may want to move things over just a tad. On this axis, we're going to have, if I hold down long enough, it makes a nice straight line. Okay, fair enough. On this axis, we're going to have energy. And let's just have this be sort of the 0 point. So I said that the HAA integral, the energy of phi A, is equal to 0. So that's sort of our 0 point. And in this case, there is no energy difference between phi A and phi B. So if you do the math, the bonding orbital is down here, 1, 2, 3, 4, 5. And each block is 1 energy unit. We're going to sort of do this to scale. So this is our bonding orbital. And the energy difference between these two, that energy difference 1, is minus 5 energy units. Whereas the antibonding orbital, 1, 2, 3, 4, 5, 6, 7, about 7.5, is substantially higher than the bonding orbital is low, and that energy difference is around 7.5 units. Again, that's sort of a reproduction of what we barely did, only we're putting some numbers on it and drawing it to scale. We're going to need a little bit more space, so I'm going to pull that down a little bit. Notice that because of the overlap integral, the destabilization of the antibonding orbital is higher than the stabilization of the bonding orbital. We can also calculate coefficients, and if you did that for this particular case, you would come to the conclusion that, as with the simple hydrogen atom, the coefficients on the two atoms are identical. Makes sense because the orbital energies were identical. Similarly, in the antibonding orbital, the coefficients are going to be identical, though opposite in sign. So 0.79 phi A minus 0.79 phi B. And in both of these cases, if you do if you square both of those wave functions, the answer comes out to be 1. Okay. So if we were to draw those orbitals, let's say this is the line between A and B, we would draw an orbital where there was the same amount of orbital on atom A as on atom B. And I guess I should explain, when I draw a molecular orbital like that, what I really mean is something that looks more like this. Is that, you okay with that? It's just easier to mark the positions of atoms when we draw it like that. Okay, so let's now, we're going to skip case 2. We're going to turn the dial up to 6 instead of 11. Here is phi A, still at 0, but this time we're going to put phi B a couple of, let's see, 6, not just a couple, but 6 units down. So 1, 2, 3, 4, 5, 6. So here is phi B, lower in energy than phi A. Okay? So when we mix these two together, the bonding orbital that we form is about minus 3.2 units lower than phi b. Okay, this is an important conclusion. When the two orbitals aren't equal to each other in energy, the stabilization you get relative to the lowest energy one is not as big. Okay? Then the anti-bonding orbital, let's see, is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I lost it. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The anti-bonding orbital instead is now up here, and the energy difference from phi b up to that anti-bonding orbital is now 11.9. So when two orbitals are not equal in energy, the bonding orbital is not as stabilized, and the anti-bonding orbital is even more destabilized. And just to make things clear, this energy difference between phi A and phi B is this delta number, which equals minus 6. Okay. So that makes sense, and it may have been taught to you in the past in terms of orbital overlap. If two orbitals are close together in energy, they mix better. That's a mnemonic device for remembering the consequence of the math. When two orbitals are different in energy, the stabilization you get isn't as big as it would have been if they had been equal in energy. But there's another interesting consequence too, and that is seen in the coefficients. So I'm going to write the coefficients for phi 1 for this case where the delta equaled 6. I have them written down here in my notes, so I'm going to look them up. 0.8. Oh, sorry. 0.47 phi A plus 0.80 phi B, whereas the anti-bonding orbital is 0.91 phi A minus 0.64 phi B. Let's talk about what that means for how much each atom contributes to the molecular orbital. Looking here for phi 1, where the coefficient tells you where most of the orbital is. If those coefficients are equal, the orbital is equal on both atoms. If they're different, if one's greater than another, the orbital is more present on one of those atoms than on the other. So which of these two, phi A or phi B, has the most of this new, which of these two atoms, A or B, has most of this new molecular orbital 1? B does, because the coefficient is higher. And if we were to draw this in a similar way as we drew the orbital where the coefficients were equal, we would show a larger amount of orbital on atom B than on atom A. And if you wanted to actually draw this the way pi orbitals look, it might look something like this. Where it's like a pi bond, only it's leaning towards the atom that's lower in energy. You guys are no doubt too young to have seen the Christmas classic While You Were Sleeping. Okay, well, if you have a chance, I can't remember what streaming service it's offered on, but this Christmas you should maybe consider watching it. There's a character, Joe Fusco Jr., and he has, at one point, he asks if somebody's bothering this girl he's interested in, because it looks like he's leaning. Anyway, it's a joke that you had to be there for, so I shouldn't have bothered. My apologies. If we do the same thing for phi 2 up top, what we would see is exactly the opposite. I need to make space for myself to draw. We would see that the antibonding orbital is mostly on the higher energy atom and less on the lower energy atom, except I got the phases wrong, right? The sign, the mathematical sign, which I'm representing with shading. I didn't say that, but did you get that? Shading is representing the sign of the wave function. Okay. And if we wanted to draw that a little bit more consistently, if this is A and this is B, it would look something like this. That more of this Psi2 antibonding orbital is going to be on the higher energy atom. This is crucially important. When two orbitals mix together and they're not equal in energy, the bonding orbital looks like mostly the lower energy orbital with a little bit of the higher energy one mixed in. And the antibonding orbital looks like the higher energy orbital with a little bit of the lower energy orbital mixed in. This tells you, for example, what we've basically drawn here is the situation between a carbon-carbon pi bond and a carbon-oxygen pi bond. You already know that carbon-carbon pi bonds are not polar, whereas carbon-oxygen pi bonds are. And in organic chemistry, again and again and again, you have been told that when you have a nucleophile attack a carbonyl compound, it does so at the carbonyl carbon. You may have learned that because, oh, well, the bond is polarized and there's a partial positive charge on that carbon. You may have learned to push arrows this way because if you make a new bond with the carbon, you'd have too many bonds with carbon, so the electrons have to go somewhere. But consider it slightly differently. Consider what happens if you think of the nucleophile as having electrons and then those being dumped into the lowest available orbital for this, say, ketone, which would be this antibonding orbital, which we could call pi star. And we could call this one pi. Where is the pi star mostly? It is mostly on the higher energy atom, which is carbon. You know that carbon's higher in energy than oxygen simply because of their different electronegativities. So if the pi star is mostly on carbon, that's where the nucleophile will attack. Okay? So this kind of thinking and analysis is going to be useful to you. You're not even going to need to do any math once we get to chapter 1, but this is going to allow you to predict reactivity in unfamiliar situations simply by thinking about what the orbitals are and where they are and how much of each is on each atom. All right. Yeah? Just
to clarify, so the nucleophile will attack the higher energy orbital.
Right. The question is, will the nucleophile attack the higher energy orbital? Yeah, the whole principle in organic chemistry of nucleophiles attack electrophiles is true. Underlying that is the idea that a high energy orbital mixes with a low energy empty orbital. High energy occupied orbital or filled orbital mixes with a low energy empty orbital. We sometimes call this HOMO attacks LUMO. Have you heard those terms before? HOMO is highest occupied molecular orbital. LUMO, LUMO is lowest unoccupied molecular orbital. So a lot of, and any of you who are TAing for an organic chemistry class this semester, pay attention to the reactions and think about them in terms of HOMO attacks LUMO. And almost every time that correlates with nucleophile attacks electrophile and gives you the ability to predict what's going to happen, even if you're not sure who the individual players are. All right, other questions? Yeah.
So the nucleophile dumps its electrons into the LUMO.
Yeah.
Does that also explain? So so it explains why the nucleophile bonds to the carbon. Is that also why like a way to explain why the pi bond between the carbon and the oxygen breaks, because those electrons are going into that high energy orbital?
Yeah.
Is that-
Yeah, that's a really great way of thinking about it. I mean, the way you do these kinds of things computationally is you just draw structures and you let the computer decide what the orbitals are. Conceptually, though, I found it useful to imagine if I take electrons from the nucleophile and dump them into this LUMO, I then have to break that bond because I've killed any and all stabilization that came from that bond. Now, what we usually don't do is worry about how do I convert these orbitals that I just made into the new orbitals after the reaction happens. You can do that, and people have done that before, but it's hard to do in your brain. One way to think about it would be the electrons in the nucleophile become the new carbon nucleophile sigma bond. Yeah. All right. What else? Okay. So just taking a step back and looking at what we have learned so far in terms of fundamental principles that you can remember even if you can't do the math are, first, that electron delocalization is stabilizing. We learned that from the definition of the Hamiltonian operator. Second, we learned that when you mix two orbitals together, the antibonding orbital is more destabilized and the bonding orbital is stabilized, and that comes from the overlap integral. And then we've just, and that's the origin of closed shell repulsion, then we've just learned that the smaller the initial energy gap between two orbitals, the more stabilizing the interaction, and the bonding orbital that you make looks a lot like the lower energy orbital with a little bit of the higher energy one mixed in, and the opposite is true for the anti-bonding orbital. So with just that in mind, we're learning a lot about things. We're learning a lot about reactivity. We still have a couple of things to do in this chapter. The chapter goes more into computational chemistry than we are going to. But the details are important. We're going to learn now the origin of the Pauli exclusion principle. Do you remember that from General Chem? What is that?
You can't do spins the same.
Okay, two electrons can't have the same spatial distribution and the same spin. Or one orbital can accommodate two electrons but with opposite spin. Actually, that's an oversimplification because the oppositely spinned electrons, those are two different wave functions, one with plus 1/2 spin and the other with minus 1/2 spin, but they have the same spatial distribution. We're going to learn where that comes from. And then the second thing we're going to learn, I don't know if you remember something from general chemistry, is called Hund's rule, which is if you have two orbitals equal in energy, you fill them up how? No, you're told it's better to parallel spins and then start filling in the others. I don't know about you, but I've always been unsatisfied with rules that end in that involve some guy's name, because, and I guess some person's name, because why should we believe it just because they said so? And so we're going to learn where that comes from. The math is going to be a little bit hairy, but it's important enough that I think we need to do it. But we won't go there today. We're probably going to finish up on chapter 14 next time, which is not Monday, because Monday is a federal holiday. The Benson building will be closed. If you want to be here and be doing stuff in the lab, make sure to get your 24-hour access, just to ask your advisor. But with that, we will be done. Have a great weekend, and I'll see you back on Wednesday.